So, we will now look into slightly different kind of modeling, 3D models. This is also attempted by some people, right. Now, you can again consider a unit cell, extension of this in 3-dimensional scenario. Even there has been extension of the Maxwell's models also, in like for 3 components. The example is where it will be useful is, say supposing there is some material which I will talk about maybe at the end sometime, phase change material. Phase change material which I will talk of, phase change material PCM, right, or PCM whatever you call it, phase change material. What happens is they would melt at high temperature, absorb heat. So, if you put them in the wall, they will absorb heat, and from solid state they will go to molten liquid state. And as the temperature outside or other side outside reduces, they will dissipate that heat and again solidify. Supposing I have some phase change material whose melting temperature is around 40 degrees centigrade and it is in a part of the wall, then when heat comes in, this will absorb heat and will not allow it to come inside. And when inside temperature falls down, outside temperature falls down, no heat will come inside, it will try to dissipate its heat and solidify. So, phase change material can store the heat for a longer period of time. Now, problem is such materials such as you can understand wax based materials, wax melt, right, similar sort of materials. So, but you can't, if you put it, if it is liquid, it will run away through the pores. So, they are micro encapsulated, they are capsulated, micro, they are very small size. Now, then what you will have? You will have wax or something, phase change material, and you have to have a layer, thick layer outside of the encapsulation, which is polymeric. And then you have bulk concrete, brick or whatever it is, whatever concrete particularly, not concrete, brick you can make it, So, brick, concrete, brick is anyway depending upon, so block or whatever it is. So, in such situation, it is now called 3-phase material, 3-phase material. One is a bulk concrete or mortar, then there is a polymeric layer, thin however it is, and then this material. So, conduction through this. So, then there are 3-dimensional expansion, 3-phase material, multi-phase system. But this is again I am looking right now at the 2-phase system only, 2-phase system. It is possible to extend even this kind of concept to 3-phase system. So, one can consider 2 types of pores. So, this cells for constant temperature. Now, problem with the Maxwell's model was, I did not discuss this, did not mention this, was initially it was taken only spherical pores, then it was extended to ellipsoid, right, ellipsoid actually. So, you can't have any kind of irregular shapes or anything of that kind, and problem with this model that I will be talking about, I am dealing with cubes. So, unit cell cubic you can consider, and you can look at 2 types of pores, and heat transfer through this cell for constant temperature at 2 facing boundary you can consider, right. So, I will come to this possibly, this is what it is. For example, consider a unit cube and you have pore, right, and then there is a solid in that unit cube, and this repeats itself in the material. There are several such, all such cells. So, every pore you can consider that is surrounded by certain amount of solid, and this proportion would depend upon porosity of course. So, now it is 3D of the same kind, and then you can consider another kind of pore where I have solid inside and pores or air on all the 3 sides, and this will be repeating in the, this part of it will be repeating. So, this 2 repeats itself, this 2 repeats itself in the material, and they are randomly arranged, and then you can look into their conductivities, right. So, this is called solid enclosing the pores. So, enclosing pores, you can call them as enclosing the pores, and this is this is, sorry, this other way around should be unit cells of enclosed pores actually. This is enclosed pores, the pore is enclosed here, and this is actually enclosing pores, right. There are two types. So, here the solid. Now, the material must be connected through. So, there are narrow necks. So, that pores are, if it is closed pore system, that you need not have necks, but in some cases materials are never, there will be some connected pores, there will be some unconnected pores. So, the connectivity depends of course, and this is solid connectivity has to be there, solid cannot be, all the air cannot be there, isolated solid will not be there. So, solids might be also connected where there are large quantity of pores. So, one can idealize, and this is unit cube. So, 1, and therefore, this is 1. So, therefore, the porosity is known, this volume, supposing I know the porosity, and this actual pores will be of this shape, idealized into cubical shapes, because handling cubical shape is easier, but currently one can handle anything, but this is what is originally done. So, if you take the cube, this one, if you take this particular one, right. So, volume of this one, so how much will be this length? If the porosity is P, this should be P cube, this should be, this porosity is volume of pores, this is unity. So, P is nothing but this length cube, L cube, if this is LP cube divided by 1, P would be equal to LP cube divided by 1. So, LP, P is equals to L length of the pore cube divided by 1, because 1 is the overall volume, right, unit cube. So, P LP would be equals to P to the power 1/3, P to the power 1/3, right. So, one can estimate this from the porosity, and P to the power 1/3 on this side. In this one it will be other way around, the solid will be 1 minus P to the power 1/3, because this one porosity is or rather 1 minus P is equals to length of the solid cube by 1. So, length of the solid will be 1 minus P to the power 1/3. So, that is how we can idealize this. This is idealized in this manner. So, now you want to find out the equivalent conductivity. So, what you assume? Constant temperature at two facing boundary. So, you consider constant temperature here and here, right, at this boundary, and these boundaries you assume, since it is one dimensional heat transfer, you assume that it is all insulated, it is all insulated. After all, they will be in materials where this will be repeating, this will be repeating, and this will be repeating in the other direction also. So, they are same, and you assume that there is no heat transfer, because they will have similar temperature. So, no heat transfer on those directions. Only along this direction of the heat flow in a wall or something like that, one dimensional heat transfer is, because conductivity is defined with respect to one dimensional heat transfer, and this is similar everywhere. So, you assume that they are insulated, one dimensional steady state at two facing boundary. You consider the heat flow at 4 other surfaces assumed to be 0 to ensure idealized overall 1D heat transfer with internal 3D heat transfer within the cell and the pore. Now, inside this cell there will be 3D heat transfer, I mean from the inside the cell, but nothing will go, no heat goes outside. So, that is how it is idealized, that is how it is idealized. So, this is an extension, in a way 3 dimensional extension of the series parallel model, right, and one can solve this, one can solve this heat transfer problem. How does one solve? Simply like this, right. So, this is your unit cube, heat is flowing, heat is flowing in, I mean some of them will be 0. So, this side is 0, this side is 1, this side no heat flow, Q is equals to 0, this side no heat flow, Q is equals to 0, except in this direction Q is going out, and going out Q is along this direction. This surface beyond this is 0 heat flow, bottom 0 heat flow, top 0 heat flow. 4 surfaces heat flow is 0, and only in one direction Q is flowing, coming in, and temperature difference is all idealizes to 1 to 0. And if you find out this Q value, that is the, for this unit area, that is the equivalent conductivity of the system. So, this can be done, these dimensions are given, and this can be done by this can be done by doing a simple thing, that is by using a non-dimensional form of the heat transfer equation and solve it. We are not solving it here, but so the steady heat diffusion equation is solved with finite element for two conditions, fully dry and complete saturation. So, there is water all inside. Equivalent conductivities then you can has been obtained for both types of cells in the above two condition at heat flow for unit temperature gradient along direction of flow. Right. 4 conductivities of unit cells then you will get 4 cases of conductivities. Moisture, one is saturated, one for the condition when 4 conditions, one say one condition is pores inside, solid outside, second condition is pores outside, solid inside for dry, both these for dry, and for saturated condition you will get two similar situation. So, you will get equivalent 4 equivalent conductivities of this unit cell. So, lambda represent equivalent conductivity of unit cell, because this is non-dimensional conductivity. So, that is why we did not use K. Subscript 1D, 2D represents unit cells of enclosing and enclosed pores, and use 1s, 2s for saturated condition. So, the 4 condition 1D, 2D, 1s, 2s and lambda. So, lambda 1D, lambda 2D, lambda 1s, lambda 2s values are computed using such finite element solutions for different assumed values of Ks, because it will vary with the Ks value. Air has got constant conductivity, but solids have got different conductivities. So, therefore, one can from this model solution one can generate what are called empirical equation relating relevant parameters, right. So, these empirical equations are something of this kind, that is lambda 1D, the dry condition is some constant into Ks plus B1, lambda 2D is some constant A2 into Ks, and saturated condition is something like this, and 2s. Now, this is now used by a lot of people. First you do a where you need very huge time for computation. This was not huge time for computation, but try to get some simple equations, because everybody cannot go and do finite element solution all the time. Also, it is a very simple finite element. But nowadays, where they have very large calculations, time required is very high, they develop what is called surrogate models. The surrogate models are nothing, you do a numerical modeling of some extent, obviously choosing appropriate levels of values of etc., and then fit an empirical equation which can be used by everybody. So, complex problems are even handled today, but when this was done such terminologies were, but this is a kind of, in a way one can say that something like a model, surrogate model sort of thing, which was derived from actually from computational results you obtain this. So, let us see how do the ABCDs are functions of porosity. It is A1, B1, B2, A2, C1, D1, these are functions of porosities, and they are something like this. It's some empirical relation. Somebody does wider jobs, these values might change, but for the case of bricks and concrete and such materials, not for timber, this still may give you good results. So, if you know the porosity A1, B1, which is function of porosity, A2, B2, C1, D1 and E1, these are all functions of porosity. So, C2, D2, E2, these are functions of porosity. This is given with known P and Ks solid conductivity, constant can be obtained for lambda 1, lambda 2, etc. So, these values can be obtained and you can find out lambda 1, lambda 2, right. You can find out lambda 1, lambda 1D, etc. Then how do we come to the equivalent conductivity? We will come to that. Gradually we will go to that and take an example calculation also. So, for random distribution of these two types of pores. Now, these pores are the enclosed type and enclosing pores. I do not know, I can know their proportion from experiment. Here is the advantage here, we will see that. But these two types of pores, there will be random proportion of this, and the conductivities are varying in order of, not order of linear order. If the conductivity of the lambda 1, let us say, or or K enclosed, let us say enclosed to K enclosing the pore, the solid inside here, the ratio is very large, order of 100, like upper bound and lower bound I was talking about, this order of this one I was talking about, these orders are very 100 or even much higher depending upon the value of Ks to Kp. If the ratios of Ks by Kp is very large, these values are also very large. So, therefore, you need not combine them in linear manner, linear proportion of lambda, which we did. We said lambda into 1 minus lambda, rather you might take in geometric proportion, for random distribution you can take geometric proportion, right. So, it is a better way to take this as a geometric or geometric mean. So, equation combining these two cells are combined to get overall effective thermal conductivity of the material in both dry and saturated states, and let us say how it is. So, unit cell, let us say F is a fraction of enclosed pores, where pore is inside, solid is outside. If this is the F, then 1 minus F will be the proportion of other type of enclosing pores, right, pores outside. So, I can combine this, and this is combined in this manner, equivalent dry divided by K solid, into this is geometric mean. Geometric mean is to the power. Geometric mean, how do you take? Supposing I want to take geometric mean of A and B, it is A to the power half, B to the power half. Arithmetic mean will be A plus B divided by 2. Supposing it is weightage factor is not half, it is 0.3 A, 0.3 A plus 0.4 B. So, weighted average, how do I find out? Like simply the weightage factors will be 0.3 and 0.4, but in case of geometric means this will go to the power, because in geometric means when something is varying in geometric progression, say 2, 4, 8 etc., your shift size, you take log. So, log 2, next one will be 2 log 2, then this will be 3 log 2. So, the log varies in arithmetic progression, log varies in arithmetic progression. So, if you take so therefore, the coefficient is 2, 3, this varies in arithmetic progression. So, f into log of if you combine this will give log of lambda 1 d plus 1 minus f into log of lambda 2 d is equals to log of d or whatever it is. Then if you can take this to the power and this also to the power, and since log of these two are added, then the product will come. So, this is what would be derived. Geometric average I am taking, weighted average geometric mean I am taking, because the values very high and I am assuming a random distribution. So, according to some proportion. So, f is that fraction. Similarly, for saturated condition I can do like this, saturation condition I can do like this. Now, this can be experimentally determined, fully saturated and dry conductivities can be experimentally determined. Ks may not be known, because you cannot make a material 0 pore. No material, real material will not have 0 pores, either you take concrete, brick, etc., etc. And this can be possibly determined with experiment, but generally one can treat them as an unknown at the first place, right, treat them as an unknown at the first place. So, there are 2 experimental results available and 2 unknowns are there, because same material I have saturated it, got the experiment done, dry it and do the experiment. So, there are 2 unknowns and they can be actually estimated from experimental results of conductivity of the source dry and solid. And once that is done, for future people they do not have to do that, they have to use the model only. So, to arrive at the model can be determined and if f is known. So, that is what it is. So, for example, if you look at these solid conductivities, one could estimate them. One could estimate them from measurements. Supposing I have these two equations available, KED, KS, dry condition, saturated condition, this is available, and these 4 which I have determined earlier, then 2 unknowns I can actually obtain, Ks and this I can obtain from these 2 equations together, doing with a little bit of trial and error, because this is is transcendal. You can't straight away, it's not, you can't obtain this. You can find out the ratio of these 2. So, KES by KED I can find out. If I want to solve for f, this will be what? Lambda 1d to the power lambda 1d by lambda 1s to the power 1 minus f multiplied by lambda 2s divided by lambda 2d divided by lambda, I am just finding out the ratio of Ks. So, lambda, this would be s, right, this would be 1 k, this would be 1 s divided by 1 d to the power, and this is 2 s divided by 2 d to the power f, and this is known to me experimentally. Take log of both sides. This has been obtained from the model, these 2 have been obtained from the model. So, I can find out the f, because it is now an equation only in f. Let me just redo this. Let me just redo this. What I am saying is KED by KES experimentally or KES by KED experimentally I can determine, and this will be lambda 1d by lambda 1s to the power, or 1d by 2d. The formula was, if I look at this formula, if I look at the formula itself, 1d to the power 1 by f KED. KED is, just let me write the full thing, KED by KES I am trying to write. So, this will be lambda 1d to the power 1 by f 1 minus f lambda 2d to the power f, and this will be lambda 1s to the power 1 minus f multiplied by lambda 2s by to the power f. So, this is experimentally known, this is experimentally known, and this right hand side I can write as lambda 1d by lambda 1s to the power 1 minus f multiplied by lambda 2d by lambda 2s to the power f. So, if I take log of KED by KES is known to me experimentally, take log of both sides, take log of both sides, this is known to me from models, this is known to me from models, for various values of Ks I have found it out. So, Ks is unknown to me at the moment, but does not matter, for same case I will find out, and I can really determine f, and once I have determined the f, calculate this value back for given value of, experimentally this is known to me. So, assumed Ks, I would have assumed a Ks, find out the value of f, use that value of f, check for the value of Ks, if it matches fine, otherwise this kind of trial and error I can find out both Ks and Kf for various cases, and this has been done for various materials. And if you do this, say for quartz sand, quartzite aggregate both, you find this fraction of enclosed pores where it idealizes, and solid conductivity is 4.83, some sort of K, these values can be obtained, density ranges or something of this kind, different sands, different sands and from different sources, and ranges of porosity one can measure also by water permeable porosity. Simply porosity can be measured by, I will just tell you how do you measure. I think I might have told somewhere, ASTM procedure C650, I think, water permeable porosity you can find out. Make a block, put it in water for 48 hours, right. see the mass change and put it for another 24 hours and see the mass change. If the mass changes in two cases are not very different, then you assume that is the saturated state. Then boil it for 6 hours, all pores will be filled in. So, completely saturation would occur, because even the fine pores where water was not able to go. So, you can find out. So, then measure its volume by suspended apparent weight in immersed in water. So, volume of water displaced you can find out. So, you can actually find out its volume. Since the volume is known, water volume is known, specific gravity of water we assume, knowing the temperature is not varying too much, and then you can calculate the volume of pores. So, permeable porosity can easily be found out. Impermeable porosity would be difficult to find out. For that you have to grind the solid into powder, find out the specific gravity. The volume is known. If you find out grind the solid into powder, find out specific gravity, total volume is known, right, mass is known, mass divided by the specific gravity will give you the volume of the solid alone. Overall volume is known, volume of the pores can be found. So, that is how you go about it, find out the pores, and you can then, using this porosity value, because P was needed in the model, Ks has been estimated from the P values, because in the model A1, A2 etc. are function of P. I will just take an example and show you, right. So, solid conductivity of fire bricks, clay brick, aerated concrete, fly ash bricks, and their fraction of enclosed pores, range of densities, range of porosities. This can be determined, or they can be determined or determined. So, you can use this model to find out, let us say, conductivity of clay bricks with porosity 30%. So, if you know the permeable porosity for different types of, for example, clay bricks, we know the solid conductivity is 2.56. Fire bricks is materially different, because they have got larger amount of alumina. They are taken from deep below the ground. So, they have larger amount of alumina, and therefore, their conductivity of solid is different. Aerated concrete has got, generally they will have a lot of other material added, common sand and such material, and effective conductivity of the solid turns out to be this, because the pores must be also included in this. Fly ash brick solid conductivity seems to be lower, because fly ash themselves have got low specific gravity. So, this is but you can determine this. Let me see if I have, I will come to this example later on, but I think yeah. Now, this enclosed pores you can also determine from Mercalli intrusion porosimetry. So, this like F is determinable, P can be determined, porosity can be determined, Ks you cannot determine, but F can also be experimentally determined by Mercalli intrusion porosimetry, where what happens is you inject mercury into specimen under pressure. So, it follows a path like this, it might follow a path like this, this is pressure. As your pressure increases, volume of intrusion increases, and when you release it, I will discuss this in the next class again. When you release it, it follows, it does not follow the same path, it follows a path like this, it follows a path like this, it follows a path like this. Some of the mercury is entrapped. This entrapped mercury is a measure of the pores which are enclosed by solid, that is why they could not come out, pores of this kind. This is a measure of this kind of pores, which could not were pores of this kind. Pores of this kind, where mercury entered, but the total mercury could not come out, it came out only when the at certain point through this, but lot of mercury is trapped. So, therefore, that is a fraction of this. So, F you can, so fraction of this type of pores you can find out from Mercalli intrusion porosimetry, and this shows the result of experimental results of Mercalli intrusion porosimetry results. This shows the kind of relationship of this is called retention fraction in Mercalli intrusion porosimetry, and this is the enclosed pores. This is the fraction. So, they vary, some sort of relationship exists. One can get a rough estimate of this. Okay. We will stop here. Next class we will look into this from solve an example and continue with this one.